Hey, how's it going, everybody? Okay, so today we're going to continue working with our graphing, and now we're going to start looking at graphing quadratics. But before we do that, we need to jump back a little bit and just review a couple of concepts that we've done previously. I touched on them in class. I want to go through them a little bit more thoroughly here so that if there's any questions that get handled here versus when you actually have to start using some of these skills. Okay, and the first one is this idea of multiplying binomials. And many of you were taught using a different method, which I prefer not to use that language in my classrooms. So for this course, all I want you to do is to multiply binomials the way that I'm going to show you, using generic rectangles. And it'll pay off at the end. It might seem a little bit cumbersome or difficult now, or too much work, because the other way might seem shorter. But at the end of this chapter, you'll see how it all comes together and why it works best if you are using the model that I'm using. Okay, so the model we're going to be using is the area model. And so what we're going to do is we're going to draw what I call a generic rectangle. And it looks something like this every single time. We draw the same model. And it doesn't matter what you do. You put one on the wall and one on the side. So I'm going to put x plus 3 on the wall, although it could have gone on the roof if I wanted to. And I'm going to put 2x plus 4 on the roof. And I call these houses, walls and roofs. And this would be a 2-story, 4-bedroom house. And then I start filling in the insides of it. So, and the way I define the inside, because the area model, it's area equals base times height. So I have x times 2x goes in this box right here. So that's going to give me 2x squared. And then I have x times 4, which would give me 4x. And then I have 3 times 2x goes in this box. That would give me 6x. And lastly, I have 3 times 4, which goes in this box, and that gives me 12. And then if I've done this well, if I've set them up correctly, I should always get like terms that are diagonal right here. So those two are the same, so I can combine like terms. And so my final quadratic is 2x squared plus 10x plus 12. And again, just a quick review, we call this a quadratic because we have x squared and nothing larger. I don't have an x cubed or an x to the fourth. X squared and nothing larger, and that makes it a quadratic. Okay, so that's the basic way that we are going to be multiplying these. So I'm going to go ahead and do another one here, another example. And I quickly draw out my generic rectangle. And this time I'm going to purposely put this one on the roof because I don't want to have that subtraction sign on the wall. If I do it like this, that looks like a fraction, and I don't like that. If I write it like this, it looks like a subtraction sign. So I'm going to go ahead and leave it on the roof because it makes it a little bit easier when I go to look at it. And then since it doesn't matter, then I can put the other one on the wall, and it doesn't matter if it's a positive sign. Now sometimes you have two negatives and you got to put one on the wall, so you got to be careful about that. Once again, I'm using the area model. So 2x times 3x gives me 6x squared. 2x times negative 2 gives me negative 4x. 5 times 3x gives me 15x. And 5 times negative 2 gives me negative 10. Remember that you can pause or rewind anytime that you need. The beauty of doing these flip lessons is you don't have to go at my pace. So if you need to pause, go ahead. And again, if I've done this well, then I should have like terms right here. And I see that I do. So I'm going to have 6x squared. And then negative 4x plus 15x gives me positive 11x minus 10. And that's the quadratic for that multiplying binomial. Okay, we're going to take a look at the next slide. Okay, going to the next slide. I see that I still have multiplying binomials, but this one's written a little bit strangely. I'm going to first make a mistake that I don't want you guys to do, that a lot of students make this mistake, is they think that they can use this, quote, distributive property with that exponent. We never distribute exponents. It is 100% incorrect for you to think or do this at any time. That goes to that one, and that goes to that one, like the distributive property. So you come up with x squared, and then negative 4 squared would give me positive 16. This is 100% wrong, and always will be. So please try and write yourself a note, or guard against that. I see that mistake a lot from students. It's, they're rushing and they do a lot of these and they think they got it down, and they just don't write it down correctly. So instead, what we want to think of it is this, is x minus 4 squared, the quantity x minus 4 squared can be written as x minus 4 times x minus 4. Now, written like that, I see that it's a binomial times a binomial, and the way that we do those is a generic rectangle, of course. And here you can see I'm going to have to deal with this negative on the wall. So I'll show you how I would have my students write that. I go x, and then I put the negative with the 4. So x minus 4 like that, and x minus 4 on top. And then I'm going to multiply to get the inside as we do with the area. So x times x gives me x squared. X times negative 4 gives me negative 4x. X times negative 4 gives me negative 4x. And negative 4 times negative 4 gives me positive 16. And once again, we see that we have like terms here diagonal. And so those are going to combine. So I get x squared, and then negative 4x plus negative 4x gives me negative 8x, and then plus 16. So you can see what a difference this answer is and this answer is. It's missing a whole term in the middle. It's missing this negative 8 right here. So you really have to guard against this, because this I see a mistake a lot from students. And this is a case they think they're doing their math correctly when in fact they're not. So you got to make sure that you realize this is a binomial times a binomial. So we do a generic rectangle. Okay, this is actually called a perfect square, by the way. Perfect square. Okay, it's a perfect square. All right, so the next one we're going to look at is the one right below it, and you see that it looks kind of similar to the one above it, except that one of them is positive and one of them is negative. So again, we're going to do our generic rectangle because we're multiplying binomials. And I'm going to go ahead and put the positive one on the wall since it's a little bit easier. And I'll put the negative on the roof like that. And remember, we draw these lines on the inside anywhere you see a positive or a negative sign. So the addition and subtraction signs, that's how I know to draw a line here and then a line here. It's because I have a negative and a positive there. Here I had a negative and there was a negative in between there, so I drew a line like that. So that's just how I know where to draw those. And now I fill in the insides. X times x gives me x squared. X times negative 3 gives me negative 3x. X times negative 3 gives me negative 3x. And negative 3 times this one should be positive 3, excuse me. And then 3 times negative 3 gives me negative 9. And lastly, we're looking for like terms, and I see that I have them right here. And so the first term is x squared. And now positive 3x and negative 3x cancel each other out and give me 0, so I don't have a b term or a middle term, and then 9, like that. So this one also has a special name, just like the top one was called perfect squares. This is called the difference of perfect squares. Whoa. What kind of spelling is that? Sorry. It's even bad for me. Okay, and it's called difference of perfect squares. Difference because the difference means subtract, and I have a perfect square here and a perfect square here. So anytime you see a perfect square minus another perfect square, that's called a difference of squares, and your factors are always going to look something like that: x plus 3, x minus 3, or x plus 4, and x minus 4. We'll worry about that a little bit later. Okay, let's take a look at the next slide. Here I have some problems for you to practice using the area model, and so you'll see that I'm directing you to use generic rectangles, not the 4-letter F word, please. I'd rather you not use that, but use the method I'm showing you. And again, it'll pay off in the long run if you don't see exactly sure why I'm having you do it that way now. By the end of this chapter, you'll see why we're doing it this way. So there's a few problems for you to practice, and if you could have those ready for the next time we meet. Take a look at the next slide. Okay, so we've been doing these kites for a while now, and I've been telling you that they're leading up to us graphing quadratics, and so here's where we're going to be the first time that we're going to see how this works. So the very first thing we're going to do, like we did before, is we're going to just color code them so that the parts that are changing the same get the same coloring. So I see that here it looks like I have a shape like that. And then that looks like this is changing the same in this one. So those, to me, when I look at these, I see that these are changing the same each time. So this shape just keeps getting bigger and bigger and bigger. Okay, so that's one of my shapes that I see. Another one I see seems to be this one over here. And then that looks like it's getting by one bigger each time, and one bigger each time. So that seems to be changing the same. And then the other thing that I see is this middle section here doesn't change at all. It seems to be staying the same each time. So that I'm going to give its own color. So there's, of course, other ways you could have broken this up. I'm not sure how you saw it, but this is how I saw it. And I always want to make sure that I'm trying to make the changes, the colors change consistently. So, okay, now that I've got my color changes, now what I do is I start comparing it to my figure number. So I look at this first one, and I see that I have 2 rows right here. I look down here and see that I have 3 rows. And then I look down here and I see that I have 4 rows. So each time I'm gaining a row. So how does that compare to my figure number? Well, here I have 2 rows, and that's figure number 1. So that's 1 more than my figure number. Here I have 3 rows, and that's figure number 2. So that's 1 more than my figure number. And 4 rows, and that's 1 more. So it looks like for this part I could write x plus 1. Because every time it changes by adding 1 to my figure number. Okay, so then I look at this side over here, and I see that this is 2 more than my figure number, and this one is 2 more than my figure number, and this one is 2 more than my figure number. So that means that this side can be written as x plus 2. So each one of these is x plus 2 here. Okay? And then I'm going to go to my red section. And I look at my red section, I see that each time I have 1 column. One column here, that never changes. So that means that's going to be a 1 right there. But going up does change. And what I see on my height here is that here it's 2 more than my figure number. Here it's 2 more than my figure number. And so here is 2 more than my figure number, and here is 2 more than my figure number. So that means that each time it's changing by x plus 2, meaning x being the figure number plus 2. And the last thing that I notice is that my green never changes. So I'm always going to have 3. Whoops, that's a terrible 3. I'm always going to have, try that again, 3 green ones. Okay, so now I can use the area of these shapes to write my equation. So for the blue, I have a little bit better. For the blue I have x plus 2 times x plus 1, because the area of a rectangle is length times width. For the red, I have 1 times x plus 2. And for the green, I have 3 every time. So the blue, I'm going to do a generic rectangle for, like we were doing just a second ago, because I need to find the area of that. So I'm going to draw that real quick. And we say x plus 2 and x plus 1. So that's x squared, x, 2x, and 2. So for the blue area, I have x squared plus 3x plus 2. And for the red, I just have x plus 2. And for the green, I have 3. So now if I add all these together, if I add my blue, my red, and my green, I get 2, 4, 7. Whoa, terrible. I get 7 ones. I get 3, 4 x's. And I get 1 x squared. So that's going to be x squared plus 4x plus 7. So that would be the rule or the equation for this shape. Now we're going to look at is how does that look, what's that look like in a graph? Okay, so you see here I have the equation y equals x squared plus 4x plus 7 from the previous page, and we're just going to do a t-chart real quick. So I'm going to do the work over here, and then I'm going to erase it because I need this space to draw my graph, but I want to show you the work that I'm doing as I fill in each one of these. Okay, so the first one we're going to do is going to be the 0. So I plug in 0 for x squared and 0 for x. Well, those are both zeros, so then I just have 7. So that's an easy one. That's 7. And then I'm going to plug in a 1. So I plug in a 1 here. So 1 squared is 1 plus 4, that's 5, plus 7 gives me 12. And then the next one is 2. So that's going to be 2 squared plus 4 times 2 plus 7. So that's 4 plus 8 plus 7, which looks like 19. And then the next one is going to be 3, so that's 9 plus 12 plus 7. So that's 19 plus 9 looks like 28. And again, if I'm going too fast, slow me down, but I'm doing some of this in my head. So then I'm going to do 4, and that looks like 16 plus 16 plus 7. That's 32, 39. And 5 looks like 25 plus 20 plus 7, which is 52. Okay, so there we go. So that is my t-chart. And I'm just going to clean this up real quick, and then I'm going to graph each one of these on my x and y axis that I already have plotted here. And you see, while I'm doing this, you probably want to set up a graph. And I went by tens, but because I already knew that I was going to get out to 52. So make sure that you draw your graph enough so that it will get you out there. You notice that I went by ones on the bottom and by tens on the y. Okay, so now I'm going to go ahead and plot my points. So it's 0, 7, so that would be about right there. Whoops, I better get my marker working. And this is not going to be perfect, but about right there. Then I look at 112, so that looks like it's probably about right there. And then I look at 219, so that would be about right there. And then look at 328, and that looks like about there. 439 looks like there. And then 552 looks like it's up there. Okay? So as you look at this, it looks like it's pretty straight, pretty linear. But if I were to try and draw this, looks like I'm missing slightly. Okay, so then maybe I'll try these two, connect these 2 points, and then I'm missing slightly. So no matter what 2 points I try and pick, it doesn't quite go through all of these points, no matter which way I draw, because this is not a straight line. This actually would be a curved line. Now, as we spoke last week about this, I should not connect these points because I'm working off of the kites that we did before. So since I'm working off kites, there's no such thing as a 2.5 or a 1.5 figure kite. So these should not be connected. But if I did connect them, you would see that this is curving ever so slightly, just like that. Okay? So we're gonna leave it at that, but this is how our graph is starting to form from our kites, and we're not getting linear equations like we did before, but now we're getting parabolic or curved ones, and the reason we're getting those is because we have a quadratic, which means we have x squared. When you have x squared, you're going to start to get a curved graph as we have right here. All right, let's take a look at the next slide. Okay, so the next thing we need to work on in order to be able to graph these quadratics is this diamond problem. It's not directly related to graphing them, but it allows us to solve problems that we then can use to graph. So we did these once before this year, and I'm just going to go through and remind you how we did them, and then there's some practice problems on the next one. So when we do these, I call these two things the wings, and remember the reason it's called diamond problem, I never draw it, but it really technically looks like this, which is why it's called a diamond problem. I don't draw that because it's kind of hard to write inside those boxes, so you'll always see me just do an X, but I'll refer to it as a diamond problem. And the way you get this top number up here is we multiply. And the way we get the bottom number is you add. So you add this plus this to get this number, and you multiply this times the wings to get the top number. So -2 times 4 gives me -8. Whoa, that is a horrible 8. A little better. And -2 plus 4 gives me 2. So that would be the answer right there. So now look at this one, the second one. It's a little bit different because I didn't give you both wings. I gave you one wing and the top. So you got to figure, okay, what can I multiply 3 by to get 12? This is definitely a more complex problem. The kids really have to think a lot more. 3 times 4 gives me 12, and then 3 plus 4 gives me 7. And then the last one down here, similarly to the one I just did, instead of giving you the 2 wings here or giving you a wing and the top number, I give you a wing and the bottom number. Still, you're going to do this one first and then figure out what that top number is. So in order for it to be 7, this must be a 2 on the side, which means that's a 10 on top. And that's it. That's how you do diamond problems. Okay, if you look at the next page, you see several examples here for you to work on, and if you start noticing right here at E, I don't give you either wing. I only give you the top and the bottom. These are the most complex ones by far. When I don't give you a wing, I only give you the top and the bottom. These I give you pretty good hints on. These are obviously very clear, and this one's not too bad. Once I get here, you do have to start doing a lot more thinking. It's much more complex because you're looking for these 2 numbers instead of obviously looking for one of these 2 numbers. But there's a few problems for you to try if you want to work on your diamond problems. And the last slide of the night is this one. Okay, so this is where we're heading. We're heading towards a 5-point method for graphing quadratics. And those 5 points are to find the vertex. Okay, and we'll talk about what a vertex is in just a second. We need to find the roots, and I put in parentheses 2 because many times there are 2 roots. Sometimes there's only 1 root, sometimes there's no roots. So I say a 5-point method, but it's not always a 5-point method. It depends on how many roots we have. So if we have 2 roots, then we'll be finding 5 points. If we have 1 root, then we won't be finding 5 points. And if we have no roots at all, then obviously we won't be finding 5 points. But we'll look at those other special cases as we move forward. Then you'll always have a y-intercept, so we'll definitely always find the y-intercept. And then you're going to find the reflection of the y-intercept about the line of symmetry. So once you find your vertex, you can find your line of symmetry, and then there's always going to be a point that's reflected about the line of symmetry that's opposite of your y-intercept. So those are the 5 points: 1, 2, 3, 4, and 5. Now here we have an equation here, y equals x squared plus 2x minus 8. So that's a quadratic because I have x squared, and I have a graph here that I've already done that will already be able for us to look at here. So let me zoom it in here. Okay, so as we look at this graph, we can see the 5 points that we need. The first point that we have there is called the vertex. The vertex is the lowest or highest point on our graph. So right down there is the vertex. Okay, and that's a point we want to find every single time. Okay, the next one that we want to find are called the roots, and the roots are where it crosses the x-axis. So it crosses there and it crosses there. For this quadratic, there are 2 roots. So it crosses this spot and this spot, so those are my roots right there. I'm going to make that my vertex color. This is my roots color. Okay. And the last 2 kind of go together. That is, they are the y-intercept, which is right here, and the reflection about the line of symmetry. So the line of symmetry always goes directly through your vertex. So once you find your vertex, you also find your line of symmetry. So if you notice that the left side of this parabola is the same distance away from my yellow line as the right side. This blue square is 1, 2, 3 squares away. This blue square is 1, 2, 3 squares away. So this line right here is called the line of symmetry. So there's always going to be a point opposite your y-intercept the same number of boxes away. So since that was 1 away from here, then it's 1 away from there. So there's your 5 points. You've got 1, 2 for your roots. You've got the y-intercept and the line of symmetry reflection of the y-intercept and your vertex. So these are going to be the 5 points that we're going to use to graph our quadratics. Okay, that's the notes for today. This wraps up our lesson from this Friday. So go ahead and take these notes as well and do those generic rectangle problems, the multiplying binomials, and the diamond problems. And I will see you guys next week. Have a great break.